Hello and welcome everyone to this lecture. So this lecture is about physics of resistors. So by resistors we mean metals which are used as interconnects. So let's get started with a cross-sectional image of a very advanced node of microprocessors. So here what I'm showing here is a cross section of a microprocessor which is fabricated at the 14 nanometer node in the Intel Broadwell process. So this technology, in other words the microprocessors using this technology, was rolled out in 2014. Now in these cross sections what you first see is that these blocks like these blocks are also these blocks here going from the top all the way to the bottom. These layers are basically metals. So metals are conducting, they conduct current, and what you can see here is that as you go from the top to bottom, these blocks, these tapered shaped rectangular block, the tapered shaped blocks become smaller and smaller. So basically it means that the interconnect or the metals become smaller as you go deep into the towards the semiconductor. So at the bottom of this cross section you see this is the semiconductor layer, and this is actually at the heart of the microprocessor technology, the semiconductors. And here these small regions are actually what the main devices are. So these are called MOSFETs, metal oxide semiconductor field effect transistors. So we will talk about MOSFETs in great details in this class, but today's class focuses on metals. So now what you can see is that in between these metal blocks, this region, now this region is called oxides. So oxides are insulators, so they don't conduct any current. So in this cross section you basically see three different type of materials. One material, the metal, another one is oxide, and the last one is the semiconductor. Alright, so in this lecture we will focus on metals. Alright, so now the circuit elements for integrated circuits. Now the basis for all computing the integrated circuits can be divided into two classes. One is linear circuit elements. So the linear circuit elements are resistors, which are basically metals, capacitors, and inductors. So these are linear circuit elements. These are also passive. And then we have nonlinear circuit element. First nonlinear circuit element is PN junction diode, which we will also discuss in this class. And then the only three terminal device that we talk about in this class is MOSFET, and this is the most important part in integrated circuits and digital computing. So MOSFET again stands for metal oxide semiconductor field effect transistors, and these are the symbols that we use. So there are two types of MOSFETs that we have in a microprocessor. One is N type and another one is P type. So this is also something that we will talk about in this class in great details, but for this lecture we'll focus mostly on the resistors. Alright, so another way of looking into the different circuit elements is classifying them in accordance with the materials that are used. So as we saw in the cross section, there are three types of materials: metals, oxides or dielectrics, which are insulators, and then semiconductors. Now using metals we make resistors and inductors. So these two types of circuit elements uses metal. Then we have capacitors, and basically capacitors are dielectrics which are sandwiched between two electrodes. So basically a capacitor structure looks like this, where you have a metal here, then an oxide, and then on the other hand you have metal. So basically an oxide sandwiched between two metal layers is a capacitor. So a capacitor consists of to make a capacitor you need metals and dielectrics and oxides. And then finally, to make MOSFETs, the metal oxide semiconductor field effect transistors, you need metal, oxides and semiconductors, all three types of materials. All right, so now we have seen the different material systems and different circuit elements that are made with different kinds of materials. All right, so let's get to the physics of resistors, and we start with the well-known equation V equals to IR. So the Ohm's law, first described in 1820, and the main thing that it says is that if we have a voltage V across a resistor and the current that flows through it is I, then the voltage is proportional to the current that flows through, and the constant of proportionality is called the resistance. Now, based on this relationship, we can derive a number of interesting other relationships which we will be using in this class heavily. So to understand that, let's consider a block of metal shown here. So the cross section of the side of one of the sides of the metal block is A and another side is B. So the area of a cross section perpendicular to which current flows has an area capital A equals small a multiplied with small b, and also the length of the block is L. So the electric field, that is electric field in the metal, is given by the voltage divided by the length. Length is L here, and also the current density. It's another quantity that we use regularly. Current density is basically the amount of current that flows through per unit area of the cross section. This is called the current density, and this is given by I over A. A is the cross sectional area. All right, so now let's derive a number of equations. So for the sake of simplicity, here we will say that the charge carriers are positive and they have a charge of q, and this charge carriers has a velocity of v. All right, so now the current density J is I over A and I is V over R. So that gives, and then V equals to E multiplied with L. So essentially this relationship says that the current density is proportional to the electric field. Now we can write this equation like this. So the current density J equals sigma multiplied with E, and sigma is the constant of proportionality between the current density and the electric field, and this is called the conductance, conductivity. This is called conductivity. Conductivity of the metal, and this sigma is equal to this, which is L divided by R divided by A. All right. So now let's look at the current density in a different way, and let's say the N is the carrier concentration. So basically the number of charge carriers per unit volume of this metal. So the current density is proportional to the charge carried by a charge carrier, then multiplied with the velocity and multiplied with the number of carriers per unit volume. So basically V multiplied with N tells how many carriers per unit time flows through per unit area of this cross section, and multiplying with it it with Q gives the amount of current carried by these carriers per unit time, amount of charge that is carried by these carriers per unit time, per unit area. So this is J. So J equals Q Vn. Alright, and then if we equate it to sigma E, which we just derived here, then we get a very interesting relationship which says V equals sigma over Qn multiplied with E. In other words, it says that the velocity of the carriers is proportional to the electric field, and this constant of proportionality is called the mobility. So we write V equals mu E, and here the mu is called the mobility of the charge carriers, and this is a very important relationship that is used in semiconductor physics a lot. All right, so there is a very interesting thing about this relationship, and the interesting thing is that think about a charge here. Think about a charge here, and we already said that there is an electric field in the metal which is given by V over L. So this electron actually sees an electric field which creates a force on it, which is given by Q multiplied with E. Now you can imagine that if there is a force on any body, it will accelerate, meaning that say you have a mass here, say the charge carrier has a mass here, so the force on it is m dv dt, ddt of V equals QE. Now if you solve this equation, what you are supposed to get is something like this: V equals V naught plus QE divided by m multiplied with t. So basically what you should get is that the velocity of the carriers should have increased with time, but here in this relationship what you saw is that if you apply an electric field, the velocity does not increase with time, rather it stays constant. If you apply a larger electric field, the velocity will be larger, but that velocity will stay constant. But on the other hand, using Newton's laws of mechanics, you see that the velocity of the electron should have increased. So how do we resolve this apparent paradox? So this is what we have written here. Based on Newton's laws of motion, the velocity of electron should have been increasing with time, but based on the Ohm's law, what we say is that velocity of electron is rather proportional to the electric field. So how do we resolve this apparent contradiction? So the question is that the Newton's law suggests that the charge carrier should be accelerating. So basically, if you have a voltage applied across a metal, there should be an electric field, and that electric field would apply a force on the charge carriers, and as a result the charge carrier should be accelerating, meaning that the velocity should have increased with time. But in reality what happens is that the velocity of the charge carriers remains constant. So velocity V, as we have seen, is equals to mu multiplied with E is the electric field. So the Ohm's law basically says that the velocity of the charge carrier should be proportional to the electric field and it should not increase with time. So why does the velocity remain constant although there is a force on the charge carrier? So to understand that, let's think about a case where a body is falling from a high altitude through the air. So if you have done skydiving, what you would have realized is that you do not, while you are falling, you are actually not accelerating while you are falling. Rather, you are falling at a constant velocity. So your skydiving experience may actually tell you something about electrons in a metal. And the thing is that when you are falling, there is the air creates a drag on you, which essentially makes you fall at a constant velocity. It does not allow you to accelerate, it makes you move at a constant velocity. And the way to understand is to realize that when you have a charge carrier, it basically goes through in a zigzag path, meaning that it moves a little bit from here, then bumps into an atom or some defects in the metal, then it goes in and bumps again and then comes back. And then it basically follows a very zigzag path when you have an charge carrier inside a metal. So now this is the case where you have an electric field. So in that case, although it bumps into, essentially the effective displacement of the charge carrier is 0. On the other hand, when you have an electric field, what happens is that this charge carrier still bumps into the different atoms and the defects, but finally what happens is that as an effect of the electric field, after, it actually has a net displacement that happens over the time, and this distance, the distance that an electron travels between two successive collisions with the atoms or the defects, is called the free path. So that is called lambda equals to the mean value of the distance is called mean free path, and the time it takes to travel between these two collisions, you can call it tau mean free path. That is the average time between two successive collisions for a charge carrier. All right, so let's derive some relationship of the mobility based on this model, and this model is called electron gas model. So let's derive an equation for mobility. All right, so let's say the force on a charge carrier F equals m ddt of v is the velocity of the carrier, and we have a positive charge. The force on it is F equals QE. So this is the force due to the electric field, so we write it Q multiplied with E. Now again, because of the collision, that applies that puts a drag force on it, and it opposes the force due to the electric field, and this drag force is mv over t. So basically it's momentum divided by the time, a characteristic time that tells you how frequently this collision occurs. And in equilibrium, the total amount of force is 0, or the ddt of v, the change in velocity with time, is 0. So now if we equate this equation to 0, then what we get is velocity v equals q tau by m multiplied with e, and this q tau by m. This is the mobility. So we have found an equation of mobility which is q tau by m. All right. So now we can derive another relationship, that is, we have seen J equals N V Q, and then V is N Q mu multiplied with E, and this mu is Q tau by M multiplied with E. So then what we get is N Q squared tau divided by M multiplied with E. But previously what we have seen is J equals sigma E. So where sigma is the conductivity, so sigma equals N Q squared tau over M. So we get one relationship here of conductivity with respect to the microscopic parameters of the materials, and then we have another equation for mobility in terms of the microscopic parameters of the material. And remember, this tau is a characteristic time for collision of the electrons, and this term is the drag force. All right. So now let's look at what are the typical materials that are used as metal. So two popular materials that are used as metals in semiconductor technology are aluminum and copper. Now aluminum is a group 3 material over here, and copper is a transition metal which is over here in the periodic table. And the most important thing is that in aluminum it has 3 electrons in the outermost shell, and these 3 electrons participate in the conduction. And for copper we have this 4s1 in the outermost shell, and this is also what participates in conduction. It has also 10 electrons in the D shell, but D shell is usually full, so usually it's just this 4s1 electron that participates in the conduction. All right. Another material is tungsten over here, which is also used in some of the most advanced nodes. All right. So what we want to calculate is, first is the density of carriers, which are electrons in these materials that participate in the conduction. So N is the number of carriers per unit volume. All right. So the first step to calculate the number of carriers is to find out the atomic density. And atomic density means the number of atoms per unit volume of the material. So here I'm showing a crystal structure of a typical metal. Now different metal has different kind of crystal structure, but let's just, for the sake of getting a order of magnitude estimate of the carrier density, let's just consider this structure. Now what you can see in this structure is that, so first you see a cube here where each of the side is around 5 angstrom or 0.5 nanometers, and in this unit cell what you can see is that there are atoms at the 8 corners of this cube, and also there are atoms at each of the faces of this unit cell. So if you consider the cube, how many atoms are there, how many atoms there are actually inside this cube? Now what you can see is that for each of these atoms, only 1/8 of the atoms will be inside the sphere. So we have 8 atoms at the 8 corners, and 1/8 of each of the atoms are within this sphere. And but what about the ones that are on the faces of the scale? So for these atoms, only half of the atom will be inside the unit cell. So you have 6 atoms sitting at 6 faces, and each of those atoms sitting on the faces, half of it is inside the cube. So you get total 8 multiplied by 1/8 plus 6 multiplied by half. So you get 1 plus 3. So inside each unit cell there are around 4 atoms. So there are 4 atoms inside each unit cell. So the atomic density is 4 divided by the area of this cube, which is a cube, and this gives you a number of 3 multiplied with 10 power 28 per meter cube. Now for example, in case of aluminum, each atom contributes 3 electrons, so the number of carriers should be 3 multiplied with 3 into 10 power 28 per meter cube. So approximately you would get a carrier density of 10 power 29 per meter cube. So let's look at some example numbers. Now for example, in aluminum you have around 2 power 10 power 29 carriers per meter cube, and in case of copper you have around 8.5 multiplied with 10 power 28 per meter cube of carrier density. Now this is a interesting question. Which material, aluminum or copper, would you prefer to use as interconnects? Now interconnects are those things that we have seen earlier. So interconnects are metals that connect different parts of a chip, and what you want from an interconnect is that you want to provide as low a resistance as possible. In other words, the conductivity of the material that you choose should have as high a conductivity as possible. So what is conductivity? So we have seen already that J equals NQV and V equals mu E. So J equals NQ mu E, and this is again J equals to sigma E. So sigma equals Q N mu. So this is the conductivity, and then we have another quantity called resistivity, which is the inverse of conductivity. So for any interconnect material or any metal that you want to use, you want a material that has a very high conductivity or a very low resistivity. So to decide between which materials to use, aluminum or copper, what you need to calculate is the conductivity or the resistivity. Alright, so we can simply calculate the conductivity or the resistivity based on the mobility and the carrier density. So this is what we have done, and what you can see is that although aluminum has a higher carrier density compared to that in copper, the mobility of the electrons in aluminum is actually 3 times lower than that in the copper. As a result, the resistivity of aluminum is actually almost twice that of copper. In other words, aluminum has a higher resistivity than copper, or aluminum has a lower conductivity than copper, and as a result you would want to use copper in interconnects compared to that of aluminum. Alright, so now that's that. So these are the experimentally measured values of conductivity of three different materials: tungsten, aluminum and copper. Now the thing is that traditionally we have used aluminum as our metal layers for a long time, but now we are moving towards copper. Now the question is, why did we want to use aluminum rather than copper before, while we already see that copper has a much smaller resistivity than aluminum? The reason is that aluminum, it's easy to deposit aluminum and use it in the microprocessor in the semiconductor processes. Now the industry is moving towards copper because of lower resistivity, but introducing copper has its own challenges, because to use copper you have to there are many other issues of compatibility that needs to be solved. But that being said, the industry is slowly moving towards copper as the material of choice for their interconnects contacts. All right. So finally, let's finish this lecture with a fun fact. So as we were saying, that metals are being used as interconnects and contacts. So basically interconnects are the wires that connect different parts of the microprocessor. And what is interesting is that if you look at different generations of microprocessors, you will see that the total length of wires in a microprocessor is humongous. For example, in the 2007 generation of microprocessors, there were around 21.5 miles of interconnects in a small microprocessor chip. Alright, so with that fun fact, let's end this talk.